This is the first video in our series on chemistry. The learning objectives for this particular video are to identify the four main elements that we see in humans. So when you've seen things like this before, the periodic table of elements, these are all the elements that we know of. And it seems really big, broad, and intimidating, but the good news is that in human anatomy and physiology, there's actually only four of these that we really care about, and then a handful of other lesser ones. But the four big ones is what we want to be able to identify. So the four main elements in humans. The second learning objective is to name three more of these. So there's three more of these in here that we actually want to pay attention to in this course as well. And not that those three are more important than a handful of others, but those are the most famous ones that we'll see in Bio 141 anyway. And number three is that when we look at an atom itself, we want to look at the anatomy of an atom. So we want to describe the three subatomic particles. In other words, the things that make up the atom. And for each of those subatomic particles, we have to identify the charge of that particle, the mass of the particle, as well as the location within the atom. So some basic anatomy of an atom is really what learning objective 3 is. So what is chemistry? Chemistry really answers the questions, what is stuff made of? And what I mean by stuff, it means whatever you see out there in the world, whatever you see inside your body. What is that stuff actually made up of? What are the building blocks? And one of the things that really comes to my brain is when I was a kid, I used to love playing with Legos. And when my kids, who are still kids, they still love playing with Legos. Because you have these individual building blocks, but you can make so many different things. You can make castles and cars and bridges and all sorts of neat things with the same building blocks, just put together a little bit differently. So we can think of chemistry, we can think of all these elements within the periodic table as Lego blocks. And like I said, it really just four main different Lego blocks are what we care about for the bulk of human anatomy and physiology, and then a handful of other smaller, minor Lego blocks. So matter, you may have heard the term matter before. Matter is simply anything that has mass and takes up space. And that matter takes up one of three states. It's either solid, liquid, or gas. To be quite honest with you, this right here, it's really not going to be super relevant in this course, but you may see little bits and pieces of this in application in the next, in Bio 142. But in any case, definition is matter is anything that has mass and takes up space, and that matter is made up of different elements. And so there's your periodic table of elements. These are all the different elements. And I'll tell you right now, here are the four we care about. This guy H, which is hydrogen. This guy C, carbon. N, nitrogen. And O for oxygen. So these three, you see these numbers at the top, which we'll get to in another video. That number 1 up at the top, number 6 up at the top, number 7 at the top, number 8 at the top. So hydrogen, carbon, nitrogen, and oxygen. These are the big four that we really care about. So they are listed out for you. 96% of a human's mass comes from just four elements: carbon, hydrogen, oxygen, and nitrogen. And there's that visual depiction of Lego blocks here. So again, with Lego blocks, you can make all sorts of really, really cool things. And so really what that means is, look, if you've heard of different chemicals out there, it maybe more commonly used, like carbohydrates or cholesterol or fats, triglycerides, things like that. What I'm telling you then is that all those things are made up of these same Lego blocks, just kind of in different combinations. So if we start off from there, then I think what happens is that chemistry itself becomes a lot less intimidating. Because I remember when I first saw something like this, I thought, holy cow, how am I supposed to learn all that? What are those numbers and all those letters? What do they mean? But really, in biology, we get to distill it down to, as I said, just the big four. So those are the big four. Some of the other ones that we care about are these. So the 8 so-called lesser elements are calcium, potassium, sodium, etc. So calcium, potassium, K for potassium, and sodium, these are the ones that we'll actually talk about in this course. Sodium and potassium we'll talk about a whole bunch. Your brain won't work unless you've got sodium and potassium dancing around the way we want it to. Same thing with your muscles. Your muscles won't contract unless we have sodium and potassium dancing around appropriately. So when we get to those sections of this course, we'll spend more time looking at the kind of constitution and significance of sodium and potassium, as well as calcium. These are some other ones that are really, really important in human physiology, but really there's not much to say about it in the context of this course itself. Phosphorus, sulfur, chlorine, and magnesium. So these are other ones. Now there's these things called trace elements that occur in very small amounts. This is pretty much the only time you'll hear me ever mention these: zinc, copper, etc. Iron, we'll talk briefly about iron when we get into blood, which is in the next course. And then iodine, we'll just mention him because he's super heavily involved in thyroid hormone production. So we'll see him again in the next course. But what do I need you to know? What I need you to know for this course is that the big four are these: carbon, hydrogen, oxygen, nitrogen. And then the smaller three are calcium, potassium, and sodium. Just to be clear, when we say here lesser, we're not really saying that it's less important. Because truth be told, if you don't have sodium in your body doing what it's supposed to do, then you'll die. And so they're really, really important. What we mean by lesser is that they're present in lesser quantities. So this factoid, 26% of the mass comes from these four. That means, the mass, the bulk of what makes you, is actually made up of these. But it would be very difficult to say that carbon is therefore more important than sodium, just because it's present in greater amounts. Without either of them, you're going to die just the same. Okay, so now just to take a step back for just a moment, the chemistry of life, or biochemistry, because I mentioned that because we're in a biology course and we really care about the chemistry of biology, the chemistry that we need to know for biology. And so really what that means is that these are all terms that you've heard of somewhere along the way. People are on low-carb diets, whether they're going paleo or older things like South Beach. You've heard people talk about carbo loading before endurance events. Some people drink protein shakes, soy protein, rice protein, whey protein, whatever. Fish oils, maybe you've consumed these before, or you've heard that eating fish is good because of the fish oils and EPA and things like that. Olive oil. You heard of omega-3 fatty acids, which are a major component of things like fish oils. Maybe you've heard of trans fats, like on nutrition labels before, and you've heard that these are no good. This course does not talk about the pros and cons of all these things. That's not my point. But the point is that what we do is that we establish a common foundation, we establish a common vocabulary, so that if you choose to read up on some of these things, things just start making sense. When you start reading about things like double bonds or whatever, those things will make sense. So as you can see, the world cares about things like chemistry. This is an old Time magazine cover. This is another Time magazine cover. Cholesterol, it's bad for you. Eat butter, yay, butter's good for you. And so again, we're not a nutrition course, so we're not here to dissect the truths or untruths, I guess, of these claims or statements. It's simply to say, to make sense of a lot of stuff that goes on out there, we need to understand chemistry. So now, let's go into the structure of an atom. So the structure of an atom is pretty simple. You've got stuff in the middle right over here, and that thing, that middle area is called a nucleus. And then you've got other stuff that kind of orbits the outside. Now, for some of you who have some background, right now you might be saying, oh, come on, man, you know it doesn't orbit. But we're going to use that model for now to say, yes, these electrons orbit the nucleus just like planets orbit the sun. It's not 100% true, but it's close enough to true to establish the right meaning for us. Okay. If you have any questions on that kind of weird statement, ask me in class, but I want to continue with the anatomy of an atom. So right here is the nucleus. This area is called the nucleus. And what lives inside the nucleus? Well, the thing that lives inside the nucleus are these things called protons and neutrons. And the things that live outside the nucleus, right over here, orbiting, so to speak, orbiting, are things called electrons. And so these then are the building blocks. It's very simple. The building blocks of an atom are protons, neutrons, and electrons. Now, I want you to try to stick with me for just a second, because I used this example of Lego blocks before, and I said, look, one Lego block here is carbon, another Lego block here may be hydrogen, another Lego block is oxygen, and another one is nitrogen, and so much of what we are is made up of various combinations of these things. So just to let you know, things like estrogen and testosterone and cortisol, all those things are made up of different combinations of carbon, hydrogen, and oxygen. Okay? So if you're good with that, let's go one level deeper. As we go one level deeper, carbon is an example of an atom. Carbon is an atom. So carbon looks something like this. And so does oxygen and nitrogen and hydrogen. It looks something like this. Well, so what's the difference then? The difference is, well, how many protons, how many neutrons, and how many electrons do I have? It's the same ingredients. So the ingredients, or the building blocks of an atom, are protons, neutrons, and electrons. But the difference between carbon and nitrogen, or even gold and silver and these other things that we don't really mention, are simply the combinations of protons, neutrons, and electrons. How many of each do we have? In some ways you can think of it as that if you have, flour, butter, eggs, and sugar, what can you make from that? You can make a cookie. great. But you can also, with the same ingredients, make a cupcake instead of a cookie. With the same ingredients, you can make pancakes instead of a cookie or cupcakes or whatever. And so what's the difference? Well, the difference is how much sugar, how much flour, how much butter, how many eggs. That's really the difference in all those different things. And most people would not confuse a pancake for a cupcake, for example. I guess it depends how you make your pancakes, but you get my meaning here. We know that they're distinctly different things. They taste distinctly different, although kind of related because of the combination of those same 4 ingredients. So in any case, these are the building blocks. So what do we have to know about these building blocks? What you have to know about them is this. Protons are these guys, and in this particular depiction, they're indicated by this blue, and that blue dot has a plus sign in it. Protons have a +1 charge. Neutrons in this particular slide are indicated by the red dots. Neutrons have a neutral charge, so no charge whatsoever. And then electrons are these green dots, and these guys are the things orbiting outside, and they have a -1 charge. So, honestly, this is just something you have to memorize for right now. And so again, protons and neutrons make up the inside, which is called the nucleus, and protons have a +1 charge, neutrons have 0 charge, electrons have a -1 charge. I would encourage you, if this is a little bit unfamiliar, to pause the video right now and grab a scrap sheet of paper and just draw this out 3 times and label each one. P for proton with a plus sign, N for neutron with a 0 on it for neutral charge, and then E for electron with a negative charge. And if you draw that out 3 times, then you'll pretty much have this information in your brain. And so the next thing that we want to know, and so remember what our learning objectives were. The learning objectives were what is the charge? We just did that. We talked about the charge on these things, and we named the 3 of the subatomic particles. We talked about the location within the atom, and now what we want to do is talk about the mass. So when it comes to the mass, that's also similarly pretty simple. Protons have a weight, and I put weight in quotes here, or weigh in quote. How much do they weigh in quotes? Because weight and mass are slightly different. Mass is how much matter is within you, and weight is the gravitational force upon you. And so you guys know that, when somebody asks you how much do you weigh, you might say 150 pounds or 120 pounds. Whereas if you go overseas to people using a metric system, they're more interested in how many kilograms you are, which is your mass. They mean slightly different things, although commonly we use them interchangeably, for better or worse. In any case, what is the weight or the mass of a proton? It is 1 AMU. AMU stands for atomic mass unit. You can also call it a Dalton. I'm going to be in the habit of calling it an AMU. Neutrons weigh or have a mass of 1 AMU, and electrons have no mass whatsoever. So we say there's 0 AMU. And so you might ask yourself, well, how does it have 0 mass? Mass is how is that even possible? And the reality is it's not possible. The mass is actually very, 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 very small. Therefore, we just kind of round it to 0. So for all intents and purposes, it has a functional mass of 0. So there you have it. These are the 3 subatomic particles, protons and neutrons, which live in the nucleus, electrons, which orbit the outside. Protons and neutrons each have a mass of 1. Electrons have no mass. Protons have a charge of +1. Neutrons have no charge, and electrons have a charge of -1. Okay, so this slide just goes on and illustrates it again. Protons and neutrons are here inside, and then electrons here are on the outside. Now, the slide here, it says stuff inside the nucleus because I wanted to emphasize protons and neutrons. But what I want to say to you is this. I've got nothing else to say about the nucleus. Nothing else to say about the stuff that happens here, because all of chemistry happens through interaction of electrons. So this atom over here and another atom over here, if they want to form some sort of chemical bond, if they want to have some relationship, then they end up negotiating electrons. They don't negotiate protons and neutrons. Okay, I will mention that again in subsequent videos. Okay, and I think I'm going to end this video right there. Let's recap the stuff that we've covered. We've identified the 4 main elements in humans: carbon, nitrogen, oxygen, and hydrogen. Name 3 more elements that are found in lesser amounts but are really important, and we'll see later in the course. And those were calcium, sodium, and potassium. And describe the 3 subatomic particles and their charge, mass, and location within the atom. As I said, I'd strongly encourage you to draw this out, just so that this becomes as simple to you as 2 + 2. That this becomes simple and plain to you. All right, that'll wrap it up for this one.